So to continue on this heat transfer problem, again we're talking about approximating the solution as we've done in the past. We have some solution U, where this is, and it's the heat transfer problem, this is our temperature. We approximate it over the finite element as a function of nodal solutions at the endpoints or nodes of a finite element and some type of function that interpolates between those nodes. So recall we can put this ODE in the weak form. Here we have this additional term that was our time-dependent term, so we're bringing around, we're carrying through a lambda, so this is an unknown that we have to find, and here are our boundary conditions. So these are flux boundary conditions. So if you've forgotten how we got this, go back in your notes and see how we set up the weak form for these 1D problems. Alright, we're going to assume zero flux on the surface and no internal heat transfer. More specifically, we're talking about internal heat transfer, not on the external boundaries. So that's why I say I equals 1. I equals 1 typically will mean the most left point of a bar, and I equals n would be the most right end point. Those 2 points are defined here. So again, we could have flux on our external endpoint boundaries. Alright, so we can recast this weak form of ODE in a matrix form given here, where our matrices take on these integrals. And remember, I'm writing this as a function of x, but this would be something that's known. You would either be given this, or this is something you can go in the lab and characterize, measure. So that would be known. Remember, we know what these interpolation functions look like, so we can take the derivatives and get this, as well as here, C would also be known. So you can integrate this. You're just integrating a polynomial. Same thing for this second order M matrix equation. So to illustrate how we solve for lambda, let's do an example. So we're going to set up a bar with 2 elements. This allows us to get the first 2 eigenvalues for this heat transfer problem. So again, we're going to take this form of the ODE for a bar with length L. We're going to set the temperature to 0 on one side, so this would really be a change in temperature, delta T, and then our flux on the other side is going to be 0. So that includes your heat convection and conduction. And the surface may be exposed to ambient temperature. So here is your perimeter, your convection coefficient, and here's the internal conduction cross-section area. Alright, so if you take this OD, you put it in the weak form, you integrate those equations for the matrix K and M, you end up getting this form. So if you have forgotten how we got to here, go back, look at how you set this problem up for a single element, and then review how do you put 2 elements together. So you add these up in a special way, we get this relation. You also have this additional term on lambda, so this is our time-dependent term. You have your flux on the boundaries internally. We have 2 elements, so the length of each element is half the total length. And remember, here's your boundary condition on the left. Internally, we have no heat generation. And boundary condition on the right is given here. So we're saying that this flux will be solved in terms of a temperature. So plugging that in, we get an equation like this. And notice these 2 are known. So our unknowns are Q1, U2, and U3. So 3 equations, 3 unknowns. However, we can simplify this down So if you take the first equation, so if we expand this out, first term is 0, we have a u2 term from here. Notice this is 0. So the first equation is totally decoupled from u3. So you can write u2 in terms of q1. And this is then automatically satisfied. So this will give you q1 independently of u2 and u3. So this is a trick we can do for small problems. Later when we do massive computations of large finite elements, this is no way nearly as obvious, but to illustrate the point here, you can solve this explicitly and then solve these two coupled. So we're solving our delta t at the midpoint and the other right point at x equals L. So finally you get an equation that looks like this. So now we need to plug in some values for a and c and h. So to do a simple problem, we plug in these values, and here is your equation, and what's left is we need to find lambda. So you notice we don't know these temperatures, but it's equal to 0, so it's in a classical eigenvalue problem. So you just take the determinant to get lambda. You get a second order polynomial which can be solved in closed form, and we get the first two eigenvalues. So it's important to note here that in these finite element problems, the eigenmodes, meaning here two modes, it's always equal to the number of unknown nodal values.